Hello, everyone. I'd like to talk today about two hemispheres with one composite mind. To get into this, first we need to discuss what is an agent. And to me and to many people, an agent is anything that can perceive, can decide, and can act. And what it perceives is an environment, and what it acts on is that same environment. But it also has to make some decisions, but it needs to have agency or autonomy to be able to act on its own authority. So perceive, decide, and act. That's what many people think is the definition for an agent. But in today's language, many people, other people are currently using the term in a much more specific case. They think, well, if you've got an agent or if you're agentic, you have to have some large language models in there somewhere. You have to have multiple agents in there, and it has to be learning about something. It has to learn from its historical experiences. So there's these two definitions of agent going on. I think the only absolutely required ones are the first three here, but a lot of people would probably disagree and say you need all six. So the two hemispheres that I'm referring to here are both cloud and edge. Those are the two halves, and we're going to build systems that include both of those elements. And why do we want to do that? Well, because in it's a much better, much more sustainable solution in many ways. Large language models have lots of parameters. They take lots of compute to run all those parameters. That compute requires energy. That energy produces heat. You have to cool that heat. So large language models are nice and they do amazing things, but in many cases we can get by with small language models. And so they have less of a energy footprint than the large language models do. We're also going to talk about traditional AI algorithms. And those algorithms today, in many cases, can give you guaranteed optimal answers that the language models cannot. And they can also, in many cases, require less compute power to do it. They're not as flexible as the language models, but if the task you need to solve fits what they can do, that's probably a better solution right there. And again, we're reducing energy, we're reducing heating. AI, of course, is good for many things. If you can make precise measurements and recommendations, well, that's going to lead to less waste in the environment. You're going to use less water. You're going to use less pesticides. We already talked about how the language models are very energy hungry. And the cloud, even just sitting idle, takes a lot of energy. If we move things to the edge, we're going to have a lot lower footprint for energy. If some edge solutions now send everything to the cloud. Well, if you don't have to send every byte to the cloud, that's less communication costs. And then there's the whole energy savings on the whole communication pathway. Cooling is a very large part of many data centers today. It's a substantial fraction of the energy that they consume. With an edge device, you can probably get away with ambient cooling, so there's no cooling itself involved. And of course, edge devices have much lower latency because you only have to travel to the other side of the board to get your answer, as opposed to going all the way to the cloud and coming back. One of the features that I believe we're going to see in the next few years is the adoption and the rise of, some people call it composite AI. To me, it has three elements to it. It's multi-agent, it's multi-tool, and it's multi-AI. A lot of people are already doing multi-agent, multi-tool designs, and that's not particularly new. What I do think is new is the multi-AI piece. Too many people are ignoring the capabilities of some of these traditional AIs, and they don't do everything, but they should be used where they have been designed to be optimal. So large language models are one kind of AI. We talked about they take a lot of parameters and a lot of energy to compute. Small language models are also a good option. They help reduce your energy footprint, and many of them can run, some of them can run on the edge device, but there's a whole lot of other traditional AIs that can be employed. Um, and like I said, in some cases, they're a better solution. So I want to talk about a few different ways to arrange how agents interact with each other. And the first thing I want to say here is that I'm using these hats here as agents. Each hat is one agent. The hats themselves don't really mean anything in particular here, but I'm just using different hats to represent that these different agents have different roles to play in whatever we're doing. And the icon here, the gear icon, that's about a process. And a process is either one or likely a small number of agents that are working together to perform some kind of a task. So that's the icons I'm using here. So in the programming flow, it's the architecture that is deciding how agents talk to each other and what paths they can use. You can code them that way, and that's great. It works in many cases. Another somewhat more sophisticated idea is the idea of orchestration. And in this case, we have some initial agent. Here I've got the cop's hat in here, and the cop looks at it and decides which of the three agents below should he pass this information off to. Is it primarily about healthcare? Is it primarily about something else? And he will pick the agent that is executed next. So in orchestration, one agent is really deciding how to control the flow. A somewhat more sophisticated and subtle version is where the agents decide among themselves, and each agent decides for itself which other agents it's going to communicate with next. This is called a choreography. And each agent is deciding how to flow messages around. The choreography is a nice idea. It's very flexible, but it's also very challenging to debug. So if you're just getting started, I would recommend you stay with more of the programming or at least the orchestration. Save choreography to when you're more comfortable with all the things that are going on here. So let's talk about a number of patterns. One of the patterns that I really like is called deterministic core and probabilistic border. Yes, I know that's kind of a mouthful, but let's just kind of step through it quickly. So let's suppose that we have some process and we can use a traditional AI algorithm to do that. So maybe it's a classification, maybe it's a regression, maybe it's something else. But what's really happening is we have structured information coming into it and structured information coming out of it. The algorithm itself is deterministic and it's working on structured information. And that's nice. You can often get optimal answers out of this kind of a solution. However, the world is a noisy and messy place. So if you've got noisy text, noisy image, noisy videos, traditional AIs have not been very good at dealing with these kinds of messy inputs. So we have these unstructured things coming in, and we're probably going to need to use a probabilistic algorithm to even make sense of what's going on. And the goal of this agent is to convert from the unstructured, messy world into a structured, more normalized sort of a world. But then he's creating the symbolic input that's going to go into the traditional AI. If we're in a deterministic core, we can do other things as well. In this case, we've added a rules engine to take and look at some of those symbols and make some determinations. This is a deterministic algorithm, but we're in the symbolic space, in a structured space, so we can do systems and build them like this. This is actually the structure and architecture for a system that I've been recently working on. We use LLMs to process the messy text input, and then we do a number of deterministic algorithms to figure that out. And then finally, we didn't do this in my project, but we easily could have. If you have these symbolic outputs, structured outputs from the cap there, you could go back into another probabilistic algorithm to fluff it back up into nice text, images, videos, whatever you want to do. So the idea here is that in the core of this, we want to use deterministic algorithms. And part of the reason for that is they don't hallucinate. You can be sure that what's going on here. But on the core, to deal with the real world, the messy world, we need to put some probabilistic elements to deal with that. One point to notice here is that if the input probabilistic algorithm messes up, we can see it by examining the symbols that it's output, and we can control what's going on. We can ensure that the probabilistic algorithm is doing what we really wanted it to do. We don't have to worry about, the rest of some other LLM trying to figure out what's going on here. Let's talk about some data flows here. If we have just, call return, that the main program calls agent 1 and gets the data back, and then it calls agent 2 and gets his data back and passes it on, that's certainly a way to do programming. We've been doing it for decades. If you've only got a single processor, this might be the one that you want to choose. But if you have multiple processors, and particularly if they run at different rates, what you might want to do is a more asynchronous architecture. And in this case, we would be using queues, perhaps MQTT kinds of queues, and agents read from their input queue and then they write to their output queues. And this just gives a little bit more flexibility to how the agents are running. Timing issues become somewhat less important here, less hard to debug. Another version of this is you might want to put some state spaces into the message flows. And why would this be a great idea? It's a little subtle, but if you have a state stores like this, you know who wrote that record. And we also know who's reading those records. So it's a little bit easier to reason about what's going on in the flow, and it's a little bit easier to debug it. So again, some of these are not that radically new ideas, but there's different ways to approach how the agents are going to communicate with each other. Another approach, of course, is that we want to use detailed computations, intense computations up in the cloud where we have the compute resources to do that, and we have the data storage resources to store all the information that we want to process. Down on the edge, you don't have as much compute, you don't have near as much storage, so you might run similar algorithms down there, but you're probably only going to get more of an approximate answer. So why don't we run everything in the cloud? Because the cloud can be intermittently connected. The communication lines might drop between the edge and the cloud from time to time for various reasons. But on the edge, it's always on, so that's really nice. So that's another set of reasons for why you might push one agent to the cloud and one agent to the edge. This is another design pattern that I really like. It's called the designer checker. So we have a designer agent, and this could either be a large language model or it could be a human, and it's designing an algorithm. It's producing a version that's supposed to satisfy all the constraints. Now, LLMs hallucinate. People get tired and they make mistakes. So what is generated may not be quite right, but it is a full design. So that output then goes to some checker algorithm. And in many cases, we would like the checker to run some deterministic algorithms to make sure that the output generated by the designer actually satisfies a number of the different requirements that we have. And this could either be from equations or some symbolic system. And that's a great way to make sure that you don't have any hallucinations left in the designer's output if possible. And that only really works if the designer's output is structured output. If the designer's output is unstructured, you're not going to be able to use deterministic algorithms, but you might imply a different LLM to check the results of the first one. This isn't going to guarantee that you don't have any hallucinations because the LLM judge could also hallucinate, but it reduces the chance that the hallucinations are going to get through. So I really kind of like this. And I would mention that you might want to say, well, let's just make the checker a tool. I recommend against that because the designer could decide, I don't need to run this tool in this case. And so you lose the advantage of the pattern altogether. If you do it with one of these programmatic kind of situations, the output of the designer must always go through to the checker. And so you get some assurances that way. This one is a little bit more about fault tolerance. So let's assume that this graduation cap agent is up running in the cloud and he's doing some deep forecasting. He's got all the compute he needs and all the storage resources he needs, but the communication line drops for some reason. So the best data that was flowing down to the edge before now isn't flowing down for some period of time. On the edge, you could say, well, what I'm going to do is I'm just going to use the last best estimate that I had, and I will continue to do that. But if there's a period of time where that's going on, you're still using data that's stale, and it's getting staler and staler and staler. In some cases, you might be able to have a simple agent on the edge, this simple forecaster. He's not as good as the one up in the cloud, but he can project data forward a little bit. And so if you use this pattern, this simple forecaster is looking and saying, hey, I didn't get any input from the cloud. I'm going to do my own forecast, and I will keep doing that as long as there is no information. But as soon as I get information back connected to the deep forecaster, I'm going to switch and start using his information, and I'm going to update my own tables so that I know where I'm actually at. So this is a way to add some kind of fault tolerance to your system. So there, we've talked about the agents, but now let's look a little bit about some of the processes. Again, a process here is one or more agents, but they do some kind of recognizable human function. But you might have one process that has to run before a second process. This is just a sequential relationship between them, and you can diagram it in this way. Some processes can run in parallel. They don't have any interaction with each other. You can launch them both, and they go off and they do their things, and everybody's happy. But there are cases where you have a couple of processes, and they share something that can't be shared. So let's say that these two processes need to share a piece of hardware to do something. Only one process can use the hardware at a time, so these are exclusive. You have to make sure that only one of these processes is running at a time. And then, of course, you might have multiple processes running, particularly from the parallel case, and you need to merge them back together. Not a huge idea here, but these are some of the dependencies to think about and probably to design out as you're doing your architecture. So we've talked about agents acting. One of the key ideas is, do we want the agent to act? Do we allow the agent to act? Do we allow it to have agency? Do we allow it to have autonomy to work on its own? So you get to these decision points where the agent has to make a decision to go left or go right or do A or do B. Do we give the computer agency to make that decision on its own? Or do we say, no, we need a human to make this decision? And in any architecture, you're probably going to have a lot of different decision points. Some of them you may give full autonomy to the computer and say, yes, I want you to make the decision, but other more carefully considered ones require human agency to make that decision. So this is all about putting agents in or humans in the loop. So the human's job in this thing is to validate or review what the agents have done before it, to approve it, to maybe actually guide what's going on. And this is just getting us into the whole idea that the agents of the humans are collaborating together. We want to give some agency to the computer so we don't overwhelm the humans, but at certain points we want the human to be involved and to take control. So we've talked about a lot of patterns. Let's now look at how to apply some of these patterns, certainly not all of them, but apply some of these patterns to a precision agriculture application. So the first thing we're going to do is we probably want to look at the weather system, and this is the macroclimate idea. We're going to need that information to make some decision. We want to look at the microclimate. What is the soil moisture? What's the temperature? What's the pressure? What's going on there? That's information that we're going to need. And we're going to assume that we have some drones out there and they're flying around our crops and they're providing us video data or image data, and we want to take that as input as well. These agents are basically doing nothing more than perceiving what's going on in our crop environment. So they're just part of the perceive part of the agent system. Next, we want to make some decisions on this data. Well, one of the things we probably want to do is look at the crop health. And we're going to assume here that the crop health is based on the microclimate, how much soil moisture is out there, what's the temperature, that sort of thing. And then what is the information that we're getting from the drone? Are the leaves green? Are they brown? What's going on that way? This agent, this process is helping to determine what the crop is doing. How does that really look? We also probably want to capture history on everything that's going on here. And we want to capture that so we can look back in the future and make and understand and learn from that data that we had. So we probably want a history agent in here. This may not be a full agent. It may just be a database or a knowledge graph, something like that. But we probably want to capture that as well. Now, in this particular picture, I'm showing a single planner agent, and this planner is orchestrating the entire operation here. That's an easy way to do it. In some cases, it's easy to conceptualize what's going on, but the planner has a lot of work to do, and that is one of the reasons that you might want to split the planner up into multiple different components. But you really need to be looking about exactly what each of these components are doing. After the planner, well, we probably want to do some yield prediction. How is the crop progressing throughout the entire growing season? Is it doing well? Is it doing badly? What do we think we're going to get at the end? And of course, this is based on the current crop health and also the history that we've had from past runs. And maybe there's some compliance and reporting going on, so you probably need to do some of that. But we also, the planner is helping us determine what we need to do in the next state. And one of those things is, do we have to irrigate? What is our irrigation plan for the next period here? Also, what do we want the drones to do in this next period? Do we want them to fly at all? Do we want them to collect specific kinds of data? That's all part of the decide step. But then the final action for this entire macro process is we want to take this general irrigation optimization plan and we need to actually implement it at the detailed level. And so that's what the irrigation control is doing. And we have a plan for the kinds of things we want the drones to do, but somebody's got to figure out how to navigate those drones up and down the crop rows. And so that's what this drone navigation is all about. And then, of course, finally, why are we doing the drone navigation? So that we can now collect video in the next period about the drone. So we've got some feedback loops going on here. So like I said, this doesn't employ all of the patterns that we've talked about. Some of them would be buried inside some of these other processes. But this is a way to kind of think about how you would do a multi-agent system, a composite AI system, for a particular industry, in this case, precision agriculture. So just to wrap up here, I just want to make, a couple of more points here. Composite AI, I think, is going to be growing in importance, particularly in the next 2 to 5 years. It's about being multi-agent, about being multi-tool, and of course, being multi-AI. I think too many people are ignoring that element. There's so many kinds of artificial intelligence and machine learning out there. Too many people are ignoring a lot of those. And if you're designing only with large language models, I think you're probably wasting energy. You're probably using bigger hammers than you actually need to use. So we've covered a lot of topics here. There's many other details that I would have loved to go into, but don't really have time here. But if this has given you some ideas, it's given you some questions, I'd happy to connect with you and dive some deeper on some of these issues here. The QR code here is a link to my website at which you can contact me. Thanks for your attention.